So what I want to talk about today is circuits, and we're going to kind of go over as always, just very theoretical, and then eventually kind of build up more practical ways of doing it. So we're going to highlight what a circuit is today, and also highlight a simple series and then a simple parallel, and the pros and cons for each one, and kind of why those really don't exist. We actually have a combination of the two, but because of those pros and cons, we're going to use a little bit of each. So as a review, you have a circuit. So a circuit is pretty much a closed loop. So remember, in a battery or even in anything, electrons want to get from the negative terminal to the positive terminal, or current is going from positive to negative. Either way, it's trying to get from one place to another. You're going to help it by completing the circuit. So as you allow the electrons to travel from one end to the other, you're allowing the redox reactions occurring on both sides. I have a racetrack here to kind of demonstrate the same kind of concept. You have a start and finish. The goal is to get from the start to the finish. And what we could do is we can manipulate that electron and make it do stuff for us. So kind of like a racetrack, you can have a simple track that's really small. You can have lots of turns and make it really long. And just like a circuit, you could short it out, which is the quickest way from one end to the other. Or you can make it do stuff for us because it does have some potential energy stored up in the chemical reaction itself. And by putting obstacles or resistors or any kind of load, it's able to do some work for us. So that's the whole goal of using electricity, is that now we can make it do stuff as it flows from high energy to low energy, kind of like water in a waterfall. If we put a turbine in the way, it's as it falls through kinetic, as it turns from potential to kinetic, it could turn a turbine and produce energy, in that case more electricity. What I want to show you here is the components of electricity. So we have Ohm's Law, which we're going to finally have at the end. But to build up to it, we're going to have different things. So the first one is voltage, which is the potential difference. The main thing I want you to get from this is that at our home, the potential difference in our plugs is 120 volts. We'll eventually go over the whole progress from the power plant to our homes, why it jumps from 30,000 to 500,000, back to 70,000, down to 7,000, and then eventually down to 100 or 240. Why do we do that? The big thing later on is Tesla versus Edison, or Westinghouse versus Edison, and who won in the end. Okay, so we'll eventually talk about that, but for now, what I'd like you to know is that in our homes, the electrons have a potential, storage or potential energy stored up of 120 volts. So that's its potential. That's how much energy it has to give us to work. We can have things to up or down the voltage, but most cases it's going to work from this 120 volts. Some cases we do have 240 in our houses. So behind your dryer, you might see a plug that looks like this. So that is a 240 volts. Behind your oven should also be something like this. So most of our ovens now are electricity versus gas, so you might see a 240 volt there. So we'll kind of get to that once we get to circuit breakers, how it's done, and it's done by the two HOTS, which we'll kind of get into once we kind of talk about residential stuff. So that's the goal eventually. Now the next one is current. Current is just coulombs per second, or a better way is just amps. You don't really need to know like conceptually how much electrons are in a coulomb. It's a pretty big number. What I just want you to know is that it flows. The more amps, the more electrons are flowing. The less amps, the smaller amounts of electrons are flowing. So as we do more problems, you'll kind of get a sense of what's a lot of amps and what's not a lot of amps. But just know, here's a nice picture where electrons flow from negative to positive. But remember, conventional current, because of Franklin, is going from positive to negative. Both ways will work in our problems. It doesn't matter which way you like better or not. The only time we'll actually get a problem if you're using the right or wrong way is when we get to magnetic field that's produced by a electron current. The last thing is resistance. If we short it out, short circuit, then there is no resistance. So the electrons in a battery, so let's say this is a battery, and remember there's two reactions happening, and this reaction can only occur if electrons are traveling from one end to another. So if you add just a wire from the negative to the positive, you're allowing it to travel there as quickly as possible. So those reactions are going to occur as fast as it can. So that's why you'll heat up the wire because it's just flowing through really quickly. You'll also heat up the battery because the reactions are happening really quickly, and that's when you have no load. When you put a load on, or a resistor, what you're doing is forcing that electrons to do something for you. So whether it's plugging it in your refrigerator or a light bulb's easy because you're making it go through a filament, will heat it up, and you're producing energy that way. So that resistance to move is going to make that reaction slower, but also you're taking advantage of the potential difference between the negative and the positive. Okay, so those are the three components of Ohm's law. Here is Ohm's law, and it's actually really simple. It's V equals IR, and that's it. So voltage is equal to current times resistance, and we're going to use this relationship to kind of figure out how much amps is going to be because of its resistance, or how much voltage, and all variables. For our home though, most of the time this is held constant. Our voltage is going to be the same, and what's going to change is, because of voltage, the resistance would determine the current. Now, it's really hard to figure out how much an object is using energy, I guess, or current, because you could think of it this way. Something with a lot of voltage is a lot of energy, but you can have very little electrons that are doing it. So when you get shocked by a Van de Graaff, it's a big leap of voltage when it does jump like 3 to 4 inches. But because only a few electrons are making that jump, it's not that much energy. So you could get shocked by Van de Graaff, which is like 10,000, 5,000 volts, ain't gonna kill you. It's not gonna feel pleasant, but it's not gonna hurt you. No internal damage, no burns, nothing. It just doesn't feel good. At the same time, if you get shocked with 10,000 volts and there's a little bit more amps to it, more current, then that damage becomes a big deal. So we want to take into account both voltage and current to kind of figure out how much energy something has, or how much energy it could do. And that's when power comes in. So we're not looking just at voltage, we're not looking just at current, we're looking at the combination of the two. So when you're combining them two together, it will give us the amount of energy it has, or the work that it's capable of doing. So it's going to be joules per second, which is measured in watts, and power is the combination of voltage and current. So that's a better measurement of how much energy or how much work this thing could do for us. So in a light bulb, if it's a 100-watt light bulb, that means it's doing 100 joules per second of work for us, and it's a more measurable amount versus just looking at current or voltage, which are important as well, but this kind of gives us the overall picture of what's going on. All right, so here is an example of a typical circuit. And what I have here is a battery on the left, and this is a schematic, so instead of drawing it out, you have symbols for certain things. This is a battery. For the battery, the longer line is the positive, the shorter line is the negative. Do you have that memorized? No, but if you do this enough, you'll probably get it memorized anyway. On the right is a resistor. It has a 10 ohms to it. And from this, we could figure out a couple of things. We could figure out how much wattage this is, what is the current flow in the circuits, etc. So we have two equations. We have V equals IR, and then we have P equals IV. So remember, this is voltage, or this is Ohm's law, which is the relationship between voltage, current, and resistance. And this is how to calculate power. So for this case, we actually have 2 out of 3 of the variables. So voltage is 9. Current is unknown, but we could solve for it, and the resistor in this case is 10 ohms. All you have to do is simple algebra, so 9 volts divided by 10 ohms, and you get a current of 0.9 amps. So with this system right here, or this circuit, we have 9 amps flowing across, or 0.9, sorry, over a 9 volt battery. Now that's not really helpful because, like I said, it's hard to compare things when you have two variables. So by turning the power, it's going to give us a number that's much easier to mentally know how much energy or work this thing could do. So we're going to combine 0.9 times 9, and it's going to give us about 8.1 watts. And now this number isn't dependent on voltage by itself, because certain things will run at 120 voltage, certain things will run at 5 volts. So it just depends, but having a combination of two will kind of give us an idea of how much energy is using. And then the more we do, you'll know, okay, 8 watts is very little, or 8 watts is a whole lot. So as long as we talk about different appliances, you'll kind of get an understanding of what's a lot and what's not a lot. Another example is here are power adapters. Eventually we'll talk about what these are. These are transformers, and we'll eventually show you what they do. But here what's neat is that it has two values that's worth looking at, actually three. For the first one, it tells you how much power it consumes. So this charger, USB-C, probably for a laptop, is consuming 61 watts. Then you have this one, which looks like a iPad charger. It has 10 watts, but what's nice is it also gives you the output. So it tells you that it's the device that you're plugging in is going to charge at 5 volts at 2.1 amps. So that's cool. It actually gives us those values for us. What's another cool thing to see is the input. This will never change because this is the plug that's in your house. For us, we are 120 volts, but it's designed for other places in the world. So other places have 240 volts versus 120. But what's nice is it shows us that it could plug it into a wall. So to confirm this 10 watt, you could just plug it into its equation. P equals IV. It gave us both V and I, so 2.1 times 5.1, and I believe it's like 10.7, but let me make sure. 2.1 times 5.1, and you get 10.7 watts. So they kind of underestimated there, but you kind of get the gist. So your charger for your phone or iPad is about 10 watts. The one for your book or laptop is about 61. So remember, this is only when it's charging. So when it's idle, it's not going to consume 61 watts, but when it's charging at its max, it will. So hopefully that's a good example of kind of the theoretical, which was the one before right here, versus something more practical. All right. So now let's talk about what you guys worked with the FET. So what I liked about the FET, it kind of gives you or makes you go through two different of the circuits. You have a series and a parallel. So a reminder, series, you just have one pathway. So electron, here's positive, here's negative, whoops. Here's negative, and it is the electrons are moving this way. And for series, they're forced through all three resistors. It doesn't have a choice. It has to go through this one, and this one. So a series circuit only has one path. Now on the other way, parallel has multiple paths. So you'll look here, you have this one right here. Whoop, sorry. You have this one right here, then you have this one right here, and then you have this one right here. So in this case, you have three pathways. Electrons could choose, well, they don't choose, it's random, but they either go through R1, R2, R3, and that's it. Only one resistor in the parallel, while in the series, they're forced to go through all three. They don't have a choice. They have to go through all of them. They can't just pick one or two. All right, pros and cons. Pros for a series. It's much, much easier to make, less wires. They don't overheat. What I mean by that is every time you add a resistor, the total current actually goes down. It's part of the property, and if you get your FET and as you add more light bulbs to it, you'll notice the overall current starts to drop. And one pro and con at the same time is in a series, once that circuit is broken, the whole thing is off. Now that could be a disadvantage when it comes to like light bulbs. So if one light bulb goes off, then your whole string is gone, which is a pain. But at the same time, in order for something to turn on and off with a switch, it has to be in series. Because in parallel, if you turn off just one circuit, the electrons could still flow in the other circuits. Cons is, like I said, it's a pro and con is once it breaks, the entire circuit fails. And unfortunately, as you add more stuff, in a series, the resistance gets higher, so the current keeps dropping. So eventually the current will be so low, you won't see anything. So if you add too many light bulbs in a string, eventually it's just not going to light up anymore. Now for parallel, kind of the opposite. Has all the cons on a series, it becomes the pros of a parallel. Does not affect one another. So if you add a bunch of light bulbs, they're all going to be the same brightness. Adding another one won't affect the original one. If one of the pathways are faulty, it does not stop the other ones. So if one light bulb goes off, the other pathways are still viable, so still work. And the voltage drop is the same for all of them. So since they're all kind of directly connected to the source, they're all going to experience the same potential difference, which is nice. Because in series, as you add more, the voltage drops for each one, meaning initially the battery was 9. If you have one light bulb, it gets all of the 9. But when you have 2, they have to share that total 9. But with parallel, each resistor or each light bulb is going to get the full 9 volts. Now, the cons are it's a little bit more complicated to wire, requires more wiring. If you're not careful, if you add too much stuff on it, the total resistance is going to drop. And what's going to happen is you're going to create danger in the sense of the more pathways you create, the quicker the current is going to be. Eventually, the current might be too high for the system. So if your wires aren't designed for a certain amperage, then you could have issues. So in your house, you have to be very careful how many things you plug in, and we have something called a circuit breaker just in case you go overboard. And also, you can't manipulate the current itself. So in order to change the current within a device, so let's say you want to brighten up your room or light bulb or dim it, a dimmer or a resistor has to be in series with the light bulb. And by having that in the series, you can control how much electrons are going through your bulb. In parallel, you can't do that. In real life, you're going to have a combination of both. You're going to wire certain things in parallel, wire certain things in series. Your house is a great example. You have switches. In order to turn on lights on and off, well, those have to be in series. At the same time, most of your outlets are parallel because you don't want to turn everything on in your house in order to turn on, let's say, your coffee maker or a blender or your refrigerator. You want only certain things that you need to use on itself. So in real life, it's a combination of two, and we'll kind of go over more of that in the example problems. Here are some rules that I want you to know. It looks kind of overwhelming at first, but it's actually quite simple. Here are the rules for series, and then here's the rules for parallel. And I'm going to kind of rewrite it so it's a lot less intimidating. For voltage, all this means is that the total voltage is the sum. So you add all the individual voltages at each resistor, and you can add them up. Current is going to be same on the entire circuit. So the current at the battery is going to be the current at this light bulb and the current at the other one. And the resistance total is also the sum. So it looks kind of intimidating, but once you kind of write that and see, oh yeah, it just says a voltage of 1 plus voltage of 2 gives me the total. And this is ... because it just depends on how much stuff you have. If it's just 2, then it's just 2 things. Parallel, it's kind of flipped. Voltage is the same throughout, kind of like current was for series, and kind of like the opposite of series, instead of the same for currents, is going to be kind of like voltage, which is the sum. Now the only weird thing is this one. This is also the sum, but it's an inverse sum. And as we do problems, I'll kind of show, it's easier to show why that is, but that's the best way to think of it. All right, so if you we're going to kind of do some problems, and hopefully it will make more sense once we do the problems.